induction, I really do think it's one of those topics that people think it's way more difficult than it actually is. This is one of the easy topics. It's mechanical. It always works the exact same way. You're not going to be required to have a fantastic new idea during the exam. The questions are all the same. This one is the first of a few examples that we are going to do today. And of course, you don't really need induction for this particular example because this is just the sum of an arithmetic sequence. And we have done that before in a different video by using different techniques that were definitely not induction. But I want to use this as the first example because it is simple enough, because you already know that it is true. And after that, we're going to go ahead and do other examples of the same kind of thing, proof by induction, and specifically in these examples that involve sigma notation. So basically, the principle of induction is used to prove that a certain statement, in the case it's this equality here, that this sum is equal to this fraction, is true for all values of n. All values of n starting at n equals 1 and going through the other natural numbers, right? Because that's what makes sense in the summation here. So it's always integers. There's always a first case, which in this example is n equals 1. And after that, I want it to also be true for all the other integers. So it's valid for n equals 1, n equals 2, n equals 3, and so on, all the way to infinity. We've talked before about the fact that examples don't prove anything. So you could prove it for like n equals 7 and n equals 12 and check that it works, but that wouldn't be a proof. And you're also not going to prove it for all the numbers because there's infinitely many of those. So what do we do instead? You really have to think about this idea of dominoes falling down, okay? It's like an infinite strip of dominoes, and you're just going to make the first one fall. You're not going to touch any of the other dominoes, but you know that the first one will make the second one fall, and then as the second one falls, it's going to make the third one fall, and so on. And this goes on forever. And of course, you don't have infinitely many dominoes, but conceptually, when what you're trying to do is to prove a statement, you do have infinitely many of these statements, one for each integer value of n. And just like in the dominoes, all you need is two things. You need to make the first one fall on purpose. You actually need to touch it and push it. And also you need to know that whenever one domino falls, it's going to make the next one fall. So it's this thing, I don't know what is the number of this domino and this domino, but I know that when this one falls, the other one is also going to fall. So those two things together is how I know that all of the dominoes are going to fall. And it also is how I know that all of these statements are true, because I am going to look at the first one on purpose. And then I am also going to prove that if one of them happens to be true, then the next one also is. So this is something that you're always going to do. You're going to make an initial case separately. And I know that examples don't prove anything, but this is not an example. This is you pushing the first domino. So if n equals 1, what is happening here? If the summation starts at 1 and ends at 1 because n was 1, then I am just adding one term. It's not going to be 1 plus 2 plus 3 plus 4 because it ends at the same point where it started. So this summation is just 1. And you also want to see what happens to the other side of the equality. So this, when you plug in n equals 1, is also 1. So your initial case is proven. In terms of getting all the marks in an exam question, what you need to make sure of in this part is that you are writing really slowly, because you know that the thing that you're trying to prove here in the case n equals 1 is going to be true. So it's like a show that question. It's not about you checking if it's true. You already know it's true. It's about making sure that the person who is reading your exam knows that you went through all the steps and didn't just say, oh, I know this must be true. So the next part is when we want to make sure that we know that one domino, when it falls, also makes the next one fall. So in other words, when the statement is true for a value of n, then we are going to conclude after some steps that the same statement is also true for the next one, which is going to be n plus 1. This part can create a lot of confusion because it does look like I am assuming the truth of the exact same thing that I want to prove. But that's not exactly right, because the thing that I want to prove is that the statement is true for all values of n bigger or equal than 1. And the thing that I am assuming here is not really for all values of n, it's just for one value, which is the domino that I am focusing on right now to make sure that it's going to make the next one fall. So this assumption here is for a specific value of n. You shouldn't call it 17 or a concrete number like that, but keep in mind that it's representing just one number right now. It's not for all numbers, like in the big statement that you actually want to prove. So that is the distinction. When I assume this, I am not assuming the statement for all n. I am just assuming the statement for a particular value of n, and then I'm going to see what happens next. And in terms of getting all of the exam marks, it is important to use the word assume here, okay? Do not use a different word that you think is a synonym of the word assume. Use the word assume. This assumption is called the induction hypothesis or the inductive hypothesis. You don't really need to say these words explicitly, but that one you do need to say explicitly. And here's the thing, these are my dominoes, okay? Those two have already fallen. This one is in the process of falling, and it's going to make the next ones also fall because they are still standing up. Each domino has a number on it, which is the value of n. And right now, the domino that is in the process of falling is number 17. It's about to make 18 fall. But I'm not interested in this particular example, okay? There's nothing special about the number 17. What I really want to show is this, is that when any one of them falls, the next one is also going to fall. I want to see what happens when one of them touches the other. And because it doesn't have to be 17, let's just call it n, like I'm doing here in the assumption. Okay, so when I say that I'm going to assume the statement for a specific value of n, this is the specific value of n, the one that is in the process of falling right now. And then I'm going to do some steps and conclude that the next domino is, as a consequence of this, also going to fall. And the next one is n plus 1. If the one that's falling is n, the next one is n plus 1. But this also didn't have to be this way. You could, for example, say that the one that is currently falling is n minus 1, and then in that case, the next one is n. Conceptually, both of these choices are exactly the same, but algebraically, when you're going to actually do calculations, a lot of the times one of them turns into shorter calculations than the other one. And in this case, for this example, I think this one is going to be better from n minus 1 to n because of what the right side looks like of what I'm trying to prove. If the statement for n has an n times n plus 1, then the statement for the next one, for n plus 1, is going to have n plus 1 times n plus 2. That is a little bit more annoying than what we currently have because this one is just one distributive, and if it was n plus 1 times n plus 2, then there's more. But on the other hand, the statement for n minus 1, if this was an n minus 1, then here it would have n minus 1 times n, which is exactly the same amount of terms as this one. So it's smaller. It's going to make for shorter calculations. So this is what I'm going to choose for this example. I'm going to assume the truth of the statement for n minus 1. And I'm going to show you two different possibilities of how to work from this into the next steps. We know that in any kind of proof, we are supposed to go from the left to the right. We are not supposed to use the thing that we are trying to prove. But right now, this whole sentence is something that I've assumed. So I don't have to treat the left side and the right side separately if I don't want to, because the whole equality has already been assumed. So the next step can be to do the same operation to both sides of this equation. And the operation that I want to do in this case is to add n. The reason for that is that on the left side in the summation, I was adding 1 plus 2 plus 3 all the way to n minus 1, and the next term was going to be n. So that's what I'm doing. I am taking the terms that I'm already summing here, and I'm adding the next one. In this particular example, the next term is just n because the thing that I am summing is just k. But we are going to see in the next examples in the video that it's not always that. What it always is the term that is inside of the sum. Okay? So over here, of course, if I did it on the left, I have to do it on the right as well. And now that I've added the next term, the whole left side just became a summation again. But now it's not stopping at n minus 1. Now it's stopping at n because I added that extra term, which I can still see here. And on the right side, all I'm going to do is manipulate now. There is a sum of fractions, so I'm going to put it in the same denominator. I'm going to distribute here. When I add the two fractions, it's going to be minus n plus 2n, so just plus n. Now I'm going to factor out the n again from the numerator. And that's it. That's the thing that I wanted to prove. Of course, when you're writing your solution to an exam question, you're not going to be making the previous steps disappear from the paper like I was doing here, okay? So your final solution is not going to look like assume this, then that. There's steps in between, which are the steps that we were just doing right now. But the conclusion is this. If you assume that the domino called n minus 1 is going to fall, then as a conclusion, the domino called n is also going to fall. And that can be any numbers. So the thing is that any one of them makes the next one fall. Now, everything that you need in order to make sure that they all fall, in order to make sure that the statement is true for all n, all that you need to do is push that first domino. And that we've already done. We've done the initial case n equals 1. We already know that the first domino is going to fall. That was the initial case. And we also know that everybody else is going to fall. And then in terms of obtaining all of the marks in an exam question, now you have to write this whole thing here. This is just the same thing that I was saying, but do you really have to write down all of these words? Yes, really. And I know that this is very annoying. I agree with you. But the thing is that you are not yet in a position of just being using the mathematical induction principle in order to prove the things that you want to prove in your life. That's not where you're at right now. You're still being tested. So what's important right here in this context of exam questions is not to prove that the statement is true. What's important is to show that you understand the principle of mathematical induction. And writing these words is a big part of showing that you understand it. Of course, here in the video, this is the last time that I'm going to write these words, but just keep in mind that you have to write them at the end of all problems about mathematical induction, okay? So there are some students who are trying to maximize the number of marks that they get no matter what. So even if they are quite sure that they have not properly used induction in the question, they will write this at the end just to guarantee that last mark. I just would like to say that this doesn't work because in the mark schemes, the mark for this text always has like an observation. Only give this mark if at least, I don't know how many of the previous marks have also been obtained. So it's not like a free mark at the end of every induction question to just write this down even though you didn't do anything else. It doesn't work like that. It's an extra mark that you are able to lose by not doing this even if you did everything else correctly. There are other important details that I still have to mention about getting all the marks in the exam questions, but before I do that, I would like to show you that there is a second option for how to go from the n-1 statement to the n statement. The first one was what we just did. We worked from the assumed statement as an equation, and we did operations to both sides of the equation. The other option would be to, instead of starting from this equation, you start from the left side of the equation that you want to prove. Because now really we're going to go from left to right without using the thing that I want to prove, and the left side is where I'm at, the right side is what I want to prove, just like we did in Show That questions in the previous video, those that didn't involve induction. And the distinction here is important. The equation with n-1 is something that we have because we assumed it, but this is part of the induction principle. Now, the equation with n is the one that we want to prove. So for this one, we are going to go from left to right. I know that in the first method, I worked from both sides at the same time, but it was both sides of the equation of n-1, which is the one that I have. I'm not going to do that to the equation that I still want to prove. And then I'm pretty much going to reverse the order of all the steps that I took. Remember, at one point I added n to this sum to get to that sum? Well, now I started at that sum and I am separating the last term from the rest of the sum. Those things are still equal, but now I'm going from there to here. And I didn't start by using the assumed statement as an equation in the beginning, but I do have to use it somewhere. And the next step is where I'm going to use it, because this part here is what I'm assuming to be equal to the other side. So I'm substituting one of them for the other in the middle of a left to right proof. And now when I get here, it's the same steps that I did on the other one. I'm going to distribute, add the fractions, and factor out the n again. I didn't write down all of those steps here, but you definitely should. So if you want to point out, this is the step where induction was actually used. We took the induction hypothesis and we used it as one of the steps in our proof here. Okay, so details in order to make sure you get all the marks. You know what you were doing, you understood the induction principle, you know how to do the calculations, but are you sure that you're going to get 100% of the marks? Because there are details in these mark schemes. For example, the word assume needs to explicitly be there. There are no acceptable synonyms. And here's the next one that I find particularly annoying. I absolutely don't like this, but remember that I told you that there is a distinction between assuming the statement for a particular value in order to prove the statement is true for all values. This is important. This is exactly what tells us that I'm not just assuming the very same thing that I want to prove. But they want you to make this distinction explicitly by not using the letter n in your calculations. The letter n should be reserved for the statement that you want to prove, the big statement, the one that is for all n. And other than that, you have to use other letters instead of n. Are you thinking that this is ridiculous, that the name of your variable, if you use one letter instead of another letter, is actually going to make you lose a mark? Yes, it will. So usually what people do is to use the letter K instead of N at this point. But you see what my problem is? I can't use K because K is already the index of my sum. So I have two options here. I'm either going to choose a different letter, such as P in this example, and when you get to the end and you're writing all of those words, make sure that you say P instead of N in the words as well, okay? And I know that P is a strange letter to use, but that was kind of intentional. I know that the natural choice would have been M because it goes after N, but also they look very similar in writing, so I want to try to avoid that confusion. So anyway, your second option is to use K, which is the usual choice in these situations, and then change the name of the index variable. They can't both be K. So that works too. I don't know which one I dislike the most. I think they're both weird. I would much rather keep my N where it was and my K where it was. But anyway, I'm not going to sacrifice a mark in my exam just because of that. So yeah, that's a detail that a lot of people know about and a lot of people are careful to apply, but then they are careful in a way that makes them lose the previous one. The assume that the statement is true for a specific value of n, which in this case we are calling k minus 1. A lot of people remember that you're supposed to change the name of the variable for some reason that they don't necessarily understand very well, and then they write this instead. This is not correct. This is not the thing that you're supposed to assume. You're not assuming that n has a specific value. You're assuming the truth of the whole statement when n has that value. So it's not enough to say assume n equals k minus 1. Assume that when n is equal to k minus 1, then the statement is true. And one of the ways to say that is just to say it like this: assume this equals that. You don't have to explicitly say that you are putting k minus 1 in the place of n. This is kind of clear from the comparison of the two sentences, but you can, if you want to, you can be explicit about this by giving the statement a name. Sometimes the question itself will do this for you. But if it doesn't, then yes, you are free to do it, but you have to be explicit, okay? Don't start assuming P of K minus 1 if you never told anybody what P is. And that's what the word let is for. It's for when you're about to define something. The word assume is for saying I'm going to act as if this is true. Let doesn't have anything to do with truth. Let is a definition. I am calling by the name P, and from now on, this statement. It's kind of useful because the statements can be long and then you don't want to write them over and over again. You can use this name in that long final sentence as well. It's kind of helpful, but you don't have to do this. This is optional. What's not option is to assume the truth of a statement, okay? You are not assuming a value for n. And it's even worse when sometimes people make the same mistake, but they're also making the other mistake of not changing the letter. Sometimes people write down assume n equals n minus 1, which is just nonsense. There is no value of n that is going to make this thing true. So how can you assume it? So there's a lot of things that are optional here, and this kind of makes people nervous sometimes. You can choose to give your statement a name or not. You can choose what letter you're going to change the name of your n to. You can choose which of two methods you are going to use here, whether working from the equation or starting from the left side and going to the right of the statement that you want to prove. You can choose whether you are going to assume n minus 1 and then prove for n, or if you are going to assume n and prove for n plus 1. This choice is, I think, the one that makes people the most uncomfortable, and it does lead to some potential mistakes. It is important to understand that what you're trying to prove is what's going to happen when one domino hits the other one. So it doesn't matter if it was this one hitting this one or this one hitting this one. But it is important that it's going from the left to the right, because the initial case is going to be n equals 1. So you're going to be pushing the dominoes from the left to the right. If you assume the truth of the statement for a value and then prove that it would also imply the truth of the previous one, such as assuming n plus 1 and proving n, then you're pushing your dominoes the wrong way around. You're going to push them all the way to 1, but what's going to happen to the other dominoes? This is the kind of mistake that when a student does this, he considers it to be a very small mistake. Oh, I went from n plus 1 to n instead of going from n to n plus 1. Oh, that is so small. This is not a small mistake. This is a fundamental misconception of what the whole principle of mathematical induction is and why it works. But finally, I think I have covered all of the little details and how to get all of the marks in induction questions. So now I'm ready to go ahead and do more examples. So this is a very interesting one. The previous one was, in a sense, unnecessary because we already knew that the sum of an arithmetic sequence works that way. But for this statement, I do think that induction is the natural way to prove it. So let's start by the initial case, n equals 1. So you check that the left side is equal to 1. The right side is also equal to 1. Of course, it didn't have to be 1, right? It's just that the left side and the right side need to be equal to each other. You could have gone a little bit more slowly there and written down the sum going all the way to 1 before just writing 1 square. But what I don't want you to do is this, okay? Even though technically this is also 1, this here would be a sum that if we changed where it stops, it would be 1 plus 1 plus 1 plus 1. That's not what we want. We want to still be talking about the same sum. It's just that it's just one term of that sum. But inside of the sum, k can't be equal 1. I know that in this case, 1 is going to be the only value that the k ever takes because it starts at 1 and it ends at 1. But that's going to happen outside of the sum. So after this equal sign. But inside of the sum, it still needs to be k. You can't substitute k for 1 inside of the sum because it's still the index. So out of all of the choices that I was just saying that you have, what choices did I take here for my assumption? I chose not to give a name to the statement. This is not something that I often do. I chose to use the letter K in place of N, even though it means that I have to change the index of my sum. And I chose to go from K minus 1 to K for the same reason that I mentioned in the other example, because it simplifies what's going to happen to the right side of this equation. And by the way, take a moment to convince yourself that this 2k minus 1 here actually is correct when you take the 2n plus 1 and put a k minus 1 in place of the n. And the other choice that I am making here is that I am going to work from the equation by doing operations to both sides of the equation. The operation is always the same. It is to add what would have been the next term in that sum, which in this case it is a sum of squares going all the way to k minus 1. So the last term in that sum already is k minus 1 squared. The next one would have been k squared. So that is the thing that I am adding to both sides. Now I'm going to have to add both of the fractions here. This means that I'm going to have to do an annoying distributive over there, but that's okay. I've changed the order of the terms here, okay? Because I really only want to do this distributive. I'm going to leave the k factored out, and in fact, one of these k's I'm also going to factor out together with that one, because now minus 3k plus 6k is 3k. And I am not the best at factoring, but there are two things that help me here. The first one is that I know where I am trying to go, right? I know what the statement is that I'm trying to prove. And the second one was that this was extremely similar to the one that I had already been looking at. The only thing that changed was a sign. So it's not very surprising that here it also was the same thing, but with the changed signs. And this is it. That's the end. That's the thing that I wanted to prove. So now I go ahead and I write all of those words about the principle of mathematical induction, and I move on to the next exercise. And this one is interesting because the initial case doesn't feel satisfying. Of course, both sides of the equation for n equals 1 turn out to be equal to a half, so they are equal to each other. But if you're only looking at n equals 1, then it really didn't have to be n over n plus 1. It might as well have been 1 over n plus 1, and you wouldn't know the difference here. So it's not that the initial case is wrong. It's not that the initial case is not enough. It's just that it is unsatisfying. So it is okay if you want to do more, like n equals 2. And n equals 2 is a lot more satisfying. You end up with 2/3 is equal to 2/3, and you really see that 1/3 would have been wrong. Here I chose to keep the index of the sum as k and to use a stranger letter instead, like p. There is no particular reason for this. I'm just trying to change it up. But there is a reason why, again, I chose the p minus 1 as an assumption, which is going to lead to p as a conclusion, and it's because of what the right-hand side looks like. So I didn't want to handle p plus 1 over p plus 2. I thought that p minus 1 over p looked simpler, so I made that choice. Again, I am going to choose to add to both sides of the equation. Okay, this is a preference. I like it that way. What is not optional is that the thing to add to both sides of the equation is the next term on this thing. On the left side, I didn't even write it separately because it's just included in the new sum when it goes all the way to p. But on the right-hand side, I wrote it down. It's the thing that I already had on the left plus the new term that I am now adding to this sum, which is this fraction when k equals p. Now I want to add two fractions, so I guess I need to multiply this one by p plus 1 over p plus 1. The denominators are then going to be the same. And this p plus 1 times p minus 1 is just going to become p squared minus 1, which is really nice because minus 1 plus 1 now cancel. And one of the p's here is also going to cancel with this p. So that's it. That's the thing that we wanted to prove. So now you just don't forget to write the text at the end. Well, since we did the sum of the arithmetic sequence in the beginning of the video, we can also do the sum of the geometric sequence. Notice that this one has the ends starting at 0, okay? So the initial case is not going to be n equals 1, but n equals 0. And again, we see that in the initial case, both the left side and the right side are turning out to be equal to the same number, which is 1. This one is even more confusing in terms of the number of different letters that we're using because we also have the ratio of the sequence there, right? but I chose k as my induction variable this time, and I am again choosing to go from k minus 1 to k. So what do I need to do? I need to add to both sides of the equation the next term of that sum. That term is r to the power of k. Now I need to add both of these fractions and do distributive here. There is a term that is going to cancel, that is r to the power of k minus r to the power of k. And I can just switch the order here to be more organized. And that is what I wanted to prove. I'm done. So you see, proof by induction, I really do think it's one of those topics that people think it's way more difficult than it actually is. This is one of the easy topics in the sense that it's mechanical. It always works the exact same way, and all you need is practice. You're not going to be required to have a fantastic new idea during the exam. The questions are all the same. Well, this one looks scary. There is a factorial in there. The initial case was easy, but then again, the initial case is always easy. So let's see what we can do with the induction. This time I made a different choice, okay, just because I don't think it's gonna matter as much. And I've been doing p minus 1 in all of the exercises. So this time I'm assuming the statement for p, and I hope to prove it for p plus 1. But that doesn't change the fact that the next step that I need to do is to add to both sides of the equation the next term of that sum. So again, on the left side, that new term is already added into the sum. On the right side, it's right here because the last term of the sum is when k is p plus 1. So this is k times k factorial. And what I want to do now is to put this one and this one together, leaving the minus 1 in the end, because now what I can do with both of those terms is to factor out a p plus 1 factorial. This one is just 1 times the factorial, and then plus p plus 1 of the factorial. So here I have factored it out. 1 plus p plus 1 is p plus 2. The minus 1 is still at the end here. And this times this is just p plus 2 factorial, right? So there it is. That's the whole thing that I wanted to show. I was a lot less careful with this one. I didn't even change the names of the letters or anything, but I just wanted to see if anything more difficult was going to happen. And it really didn't. In fact, it was very similar to the previous one. This is the new term that I am adding. Then I changed the order to put it closer to the initial part so that I could factor out the 2 to the power of n. And then everything else was just simple manipulation. But this example reminds me of something very similar that I was doing in a different video. And it's not the same thing. I am using different tools in the other video because it's a different kind of problem. It's just that it reminded me of that because of the sum with the exponential inside. So I'm gonna put a little bit of that video here right now. And if you're curious, if you want to watch the whole thing, I will put the link in the description as well. Here's a trick that I really like. That's the Maclaurin series that we are used to, right? It's e to the power of x. Now, the first thing that I'm going to do is to take the derivative of that. The left-hand side is very easy because the derivative of exponential is just itself. And the right-hand side, it looks like a polynomial. It's not a polynomial because it's infinite, but it is an infinite sum of power terms. So I can just take the derivative inside of the sum as if it was a polynomial. Now this time, instead of canceling this, I'm actually going to leave it there because the thing that I'm trying to go towards is a thing that has not just a k here, but a k squared, right? So I don't want to remove that. I want to keep it there and see if I can come up with a second one to make it a square. So instead of canceling that, I'm going to multiply both sides of this equation by x. I'm going to put an x here. And multiplying by x is just going to get rid of the minus 1, right? Everybody's going to get an extra x. Now I have this, and I'm going to take the derivative again. Over there, I am going to use the product rule. On the right-hand side, again, I'm going to take the derivative inside of the sum. So this k is going to multiply by that k, making it a k squared. That is almost exactly what I want. The only thing that I don't want is this minus 1 over here, but I know how to get rid of it. It's by multiplying both sides of the equation by x again. So I get rid of the minus 1 here because everybody got multiplied by x, but I need to multiply the left side of the equation by x as well. So there you go. That was the other result that I used to prove the variance. And that's it. We can say that all of this video was just for fun.